right, so now that we've discussed the mean value theorem, we're ready to dive in and talk about the shape of functions. We want to determine when a function is increasing, when it's decreasing, when a critical point is a local minimum, when a critical point is a local maximum. And to do that, we need something called the first derivative test. Now, before we get ahead of ourselves, let me just remind you of a couple of important definitions. So a function f of x is strictly increasing. Now sometimes I'll just say increasing, but I'll always mean strictly increasing on an open interval a to b if for any y less than z in AB we have f of y is less than f of z. So the idea here is pretty simple. As we go from left to right, so if I have a point to the left of another point in this interval, then we must have that the function values have this relationship. So f of y, the point to the left, is strictly less than the point to the right. So put kind of simply in the form of a graph, here's A, here's B. What does our function look like? Like that. So if I take any 2 points, say y and z, there's y and there's z, then you see that the function values have this relationship. F of y is less than f of z. And of course, from the graph, it's very clear. But our goal is to sort of remove our dependence from looking at graphs and actually understanding what the graphs of function looks like just by looking at the definition, the algebraic definition of the function. So now I'll say we will similarly define f of x to be strictly decreasing on an interval. So all we have to do, of course, is just change this inequality. Instead of requiring points to the left to be strictly smaller than points to the right, we want points to the left to be strictly larger than points to the right as we look at from left to right on the graph of the function. Okay, so that's going to be 2 important definitions later on because, again, we want to talk about when functions are increasing and decreasing. And what we're going to do is we're going to use the derivative to give a test to see whether or not a function is increasing or decreasing on an interval. Okay, so for the rest of this lecture, we are going to assume that our function f of x is differentiable on some open interval, a to b. And we're going to be talking about the behavior of the function on a to b based on the sign of the derivative of f of x. But just to make things really simple, we're going to always assume that f is differentiable. We're not really going to get into cases, at least right now, where f may not be differentiable. Okay, we could do that, but it's just going to kind of convolute our initial picture of what we really want to see is happening in the relationship between the derivative of the function and whether or not the function is increasing or decreasing. So let's make a little table. So since f is going to be differentiable, we can talk about the sign of f prime of x on this interval. And so, of course, here I mean plus or minus. So is the derivative positive or negative on AB? Then we can ask the question, is f increasing or decreasing on AB? So here's the idea. If the derivative is positive on the entire open interval AB, then f of x is increasing over the entire interval AB. But if the sign of f prime of x is negative, then f of x is decreasing on AB. So this probably isn't too surprising, right? Because the derivative is telling you the rate of change, or in other words, the slope of the function at each point. So if the slope of a function is always positive, then it should be increasing. And same if the slope is always negative. It should be decreasing. And there's also another option, right? The sign of f prime could be 0. And if the sign of the derivative of a function is 0, so in other words, f prime of x is equal to 0 on all of AB, well then actually f is constant. It's not increasing or decreasing. It's just equal to some fixed real number. All right, so that's the basic idea behind the first derivative test. Now we still need to state what the first derivative test says for local extrema, but this is the key idea. And now all of these facts, these 3 facts, 1, 2, 3, are direct consequences of the mean value theorem. And so just to help you illustrate, why the mean value theorem is coming into play, let's actually look at why the mean value theorem tells us that we can conclude the function is increasing on an interval if the derivative is positive. Okay, so let's assume that f prime of x is greater than 0 for all x in some open interval, AB. Okay, so let's show that f has to be increasing on this interval. So what we need to do is take any 2 numbers, y, which is less than z, in the interval a to b. And now what we're going to do is we're going to apply the mean value theorem. So now it's important to note that this is really any 2 numbers in this interval, a to b. And so what we're going to have is that this closed interval is going to be contained in the open interval a to b. And also, since we're assuming that f prime is differentiable on AB, f prime is going to be continuous and differentiable on this closed interval. So we can apply the mean value theorem. So by the mean value theorem, there is a C actually contained in the open interval from y to z, which of course is still contained in the open interval a to b, such that f of z minus f of y over z minus y is equal to f prime of c. But c is a point in this interval ab, and we're assuming that the derivative is always positive. So that means that this derivative, f prime of c, is greater than 0. And now because z is greater than y, we know that z minus y is greater than 0. So I can actually multiply both sides by z minus y, and I have f of z minus f of y is greater than 0. But then adding f of y, I get that f of z is greater than f of y. But what does that mean? Remember that y and z were taken arbitrarily. They were any 2 points in this interval. But if y is less than z, f of y is less than f of z, hence f is increasing over this entire interval. Okay, so now we're ready to state the first derivative test. Now the first derivative test is a test for local extrema. And specifically, we're testing critical points. So the idea is once we take the derivative of a function and set it equal to 0, we get a list of critical points. But we don't actually know whether those critical points are local extrema or whether they're not. All we know is that they're candidates for being either a local maximum, a local minimum. Maybe they're not anything. Maybe they're something like a saddle point or an inflection point. So here's the idea behind the first derivative test. We take a critical point C, right here. And then we look at the behavior of the derivative around a critical point. Now, of course, f prime of C is equal to 0. And so if we look at kind of a number line, if we put C here, what we can do is we can look immediately to the left and immediately to the right. So one of 3 things is going to happen. Either f prime is going to be changing signs from positive to negative. So in other words, the function could be, in the first case, changing from positive to negative, like that. So it could be increasing, and then it could be becoming 0. The derivative could be 0 at c, and then decreasing. That tells us that f of c is a local maximum, okay? And all you really need to know is this little picture here. If you change from being positive to negative, you're at the top of a mountain. The second case is if f prime changes from negative to positive at x equals c. Well, in that case, if you're decreasing and then at c, or after c, you begin increasing, then you're a local minimum. And that's pretty clear from this picture. You have a valley in case 2. Now there's also a third case, the case where f prime actually doesn't change signs. So it stays increasing or it stays decreasing. So it levels off so that the derivative is 0, but instead of starting to decrease after, you actually keep increasing. So this is, of course, not a local extrema. This is some sort of saddle point. Okay, so hopefully that makes sense. If you change from positive to negative at a critical point, then you're a local max. If you change from negative to positive, you're a local min. If you don't change sign, then you're neither a local maximum or a local minimum. And so you may ask, well, why are we only testing at critical points? Well, it really doesn't make sense to test at points where the derivative is either positive or negative. Because if the derivative is positive, we just saw that the function is increasing there. So if a function is increasing, then it's not going to be a local max or local min. The only way you can be a local max or local min, remember, if the function is differentiable, then f prime of that critical point, or of C where that critical point occurs, has to be equal to 0. Okay? So again, we're assuming here that f is differentiable. Alrighty, so here we have a function g of t. And now because we're not specifying a closed interval or an open interval as its domain, we're just assuming its natural domain. And so here the domain of this function is all real numbers. There's no problem plugging any number into this function. Now, if this was, of course, t to the 1/2 or square root of t, then we wouldn't be able to plug in negative numbers. But because it's t to the 1/3, it's an odd root, we can actually plug in positive and negative numbers and 0, no problem. Okay, so we want to look how the first derivative test allows us to describe the shape of this function, specifically where the local extrema are and where the function is increasing or decreasing. So as I said before, the first step is to almost always find the critical points, or to take the derivative. And of course, that's what number 1 is. We want to find the critical points. We want to find those points that are potentially local extrema. So what is g prime of t? Now, this is a product of functions. So this should be 1/3 t to the negative 2/3 times t minus 4, and then plus t to the 1/3. Okay, so I want to set this equal to 0. But before I do that, I actually want to simplify this. Okay, so up till now, a lot of times we haven't been simplifying. But finding critical points after you take the derivative, you really want to set the derivative equal to 0 or see where the derivative is undefined. So in order to do that, we really want to simplify. So this first term I'm going to write as t minus 4 over 3t to the 2/3, and then plus t to the 1/3, well, over 1, and I'm going to get a common denominator. So I'm going to multiply the top and the bottom by 3 times t to the 2/3. And what am I going to get? Well, this is t minus 4 plus 3t, so t to the 1/3 times 3 times t to the 2/3, it's just 3t, all over 3 t to the 2/3, which this is t plus 3t, so 4t minus 4. So 4 times t minus 1 over 3 times t to the 2/3. Excellent. And so I have a clear numerator, a clear denominator. I can see when the numerator is 0, so when the whole derivative will be 0, and I can see when the denominator is equal to 0. So that would be the case where the derivative is undefined. So g prime equals 0 when t equals 1, and then g prime is undefined when t equals 0. So I have two critical points. T equals 0 and t equals 1. Okay, so we're done with part 1. So the next thing to do is to use our criterion for the sign of derivatives and the function being increasing and decreasing to tell the intervals, or specifically the open intervals, for which the function is increasing or decreasing. So let's do that next. All right, so we know the critical points we have are t equals 0 and t equals 1. So here's what I like to do. Once I have my critical points, and I want to find the intervals for which the function is increasing or decreasing, I want to make a number line. So I'm going to put t equals 0 and t equals 1. Okay. So what do I do? Now, because I only have two critical points, t equals 0 and t equals 1, I know that on this entire interval, from negative infinity to 0, the derivative can't change sign. It has to either be positive or negative over this entire interval. It has to be either positive or negative over this entire interval. And then finally, it has to be either positive or negative over this entire interval from 1 to infinity. So all we need to do is just test one value in each one of these intervals. So I'm going to come in and say I'm going to test maybe -1, maybe 1/2, and maybe 2. Okay, so recall what g prime of t is. It was 4 times t minus 1 over 3 times t to the 2/3. Okay? So let's look at -1. If I plug in -1, do I get a positive number or a negative number? Well, plug in -1, the denominator is going to be positive because I'm going to raise that negative number to the second power. That's going to make it positive. And the numerator is going to be -1 minus 1 times positive 4, so that's a negative number. So g prime of -1 is negative. Okay? But that means for this open interval, negative infinity to 0, g is decreasing. How do I know that? Well, because the derivative is negative. And I know it's negative for this entire interval because if it ever changed sign, I would have to have another critical point. But because there are no critical points between negative infinity and 0, I know that my derivative has a constant sign. It's either positive or negative. I test exactly one point, so it has to be negative. So g has to be decreasing on this entire open interval, negative infinity to 0. Let's do the same thing for the open interval between 0 and 1. What is g prime of 1/2? Well, 1/2 minus 1 is negative 1/2 times 4. That's a positive 4. So 4 times negative 1/2 is going to be a negative number. And the denominator is going to be positive. So a negative number over a positive number is negative. So g prime of 1/2 is less than 0. And now notice I don't even really care what the actual value of the derivative is. I am just trying to get a sense of whether it's positive or negative. So g prime of 1/2 is less than 0. You may also ask, well, why did you pick 1/2 and negative 1 and 2? It really does not matter. I just have to pick one number in each one of these open intervals. These were just, in my opinion, the easiest to pick. So for 1/2, g prime of 1/2 is less than 0. So g is decreasing. And that's on this open interval from 0 to 1. Again, the reason I know it's increasing over this entire interval from 0 to 1 is because the derivative is negative over this entire interval. How do I know it's negative over the whole interval? Well, if it changed sign somewhere between 0 and 1, I would have to have another critical point. The derivative would have to be 0 at some point for it to either change from being positive to negative or negative to positive. And I only have these two critical points, 0 and 1. So now let's move on to this interval from 1 to infinity. I chose to test 2. So what is g prime of 2? Well, pretty easy to see the numerator is positive. 2 minus 1 is positive 1 times positive 4. The denominator is still positive. So this is greater than 0. So g is increasing on this open interval, 1 to infinity. Okay, so we're done. G is decreasing on negative infinity to 0. G is decreasing from 0 to 1. And g is increasing from 1 to infinity. So now what we can do next is actually use this table to determine the local extrema and the absolute extrema, if there are any. So let's see how we do that. So like I said, all we need for part 3 is really this table, or this number line right here. And what I'm going to do is draw an extremely rough sketch of the graph. So I know that the function is decreasing until 0. So it's decreasing, then the derivative becomes 0. Well, actually here the derivative becomes undefined. So even though I'm not being super precise, it actually looks like we probably have a vertical tangent instead, but that doesn't really matter. Right, because the derivative is undefined, not 0 at 0. But nevertheless, it's decreasing, and then it's going to be decreasing again. Let me start up here. So it's decreasing, derivative becomes undefined, then it's decreasing, becomes 0, then it's increasing. Okay, so this is an extremely rough sketch of g of t. But that's all I need, because I'm just looking at the general shape. So the function is just going to decrease down like this, go all the way down. It's going to level out at an absolute lowest point. But notice that g of 1, so what is g of 1? So it's 1 times negative 3. So it looks like, let's see, negative 3 is a local minimum. So how do I know that g of 1, which is negative 3, is a local min? Well, it's because the function changes from being decreasing to increasing. And that's the first derivative test. So if the function changes from being decreasing to increasing, then we have a local minimum at that critical point. And so g1, which is equal to negative 3, is a local min. And now just based on the shape of the function, I can actually see that g1, which is equal to negative 3, is also the absolute min. And how do I know that? Well, because it's the only minimum, and it's increasing to the right and decreasing to the left, so there's never going to be a t value that for which I have g of t less than negative 3, because I'm starting up here, going down, I reach this minimum point, and then I'm increasing forever after. Now I don't have an absolute max, so no absolute max. Okay, so hopefully that makes sense. So the first derivative test allows me to identify the local minima. I don't have any local maxima because g never changes from being increasing to decreasing. And I know since I only have one local min and my function increases to the right and the left, that it has to be an absolute min. And because I don't have a local max, I'm not going to have an absolute max. Okay, so again, same instructions. First step is to find the critical points. How do we find the critical points? Well, we start by taking a derivative. So let's take the derivative of f. Again, this is a product of two functions, so we need to use the product rule. So we have 2x times e to the x plus x squared minus 3 times e to the x, which we can actually simplify pretty nicely. So notice that both of these terms have a factor of e to the x. So this is 2x plus x squared minus 3 times e to the x. And now I can go a little bit further, because notice that 2x plus x squared minus 3 is the same thing as x squared plus 2x minus 3, and that this quadratic actually factors. This is x plus 3 times x minus 1. So f prime is really x plus 3 times x minus 1 times e to the x. And I want you to remember a very key fact that we've mentioned before. And that's that e to the x is always positive. Always. So it can't be 0, and it also can't be negative. And that's going to be really important when we're finding the critical points, and also when we're testing the derivative to see whether it's positive or negative. Okay, so what happens if I set f prime equal to 0? Well, we already said that e to the x can't be 0. So by the zero product property, we better have that either x plus 3 is 0 or x minus 1 is 0. But that tells me that I have two critical points. X equals negative 3 and x equals 1 are critical points, or CPs for short. Okay, and now remember, finding the critical points is essential because the critical points are going to partition up the domain of this function, which the domain of this function is all real numbers, into open intervals where the derivative is either positive or negative on each one of those open intervals. And that's what we need to do next. Okay, so again, our critical points are x equals negative 3 and x equals 1. So let's draw our number line. And we'll plot negative 3 and we'll plot 1. Okay, so now we want to test some points. So I need to test a point to the left of negative 3. So let's just do negative 4. The easiest point between negative 3 and 1 to pick is probably 0. And then to the right of 1, let's pick 2. Let me write down what f prime of x is, just so we have it. So f prime of x was equal to x plus 3 times x minus 1 times e to the x. Okay, that's good. So here we go. Let's test f prime of negative 4. If I plug in negative 4, well, negative 4 plus 3 is negative, so we get a negative. Negative 4 minus 1 is also negative, so negative times a negative is positive, and then e to the x is always positive. So I think all in all, f prime of negative 4 is positive because we have a negative factor, and a positive factor. Now for 0, we're going to have a positive factor, a negative factor, and a positive factor. So that's one negative and two positives. That makes a negative. Now for 2, we're going to have positive, positive, positive. So f prime of 2 is positive. So what does that mean? That means f is increasing. From negative infinity to negative 3. F is decreasing from negative 3 to 1. Then f is increasing again from 1 to infinity. Okay, and same story. We know that f is increasing or decreasing on each one of these intervals because we know that the derivative is either positive or negative, and we have identified the only critical points. So those are the only points where the derivative can change sign. So we're done with part 2. Now, it should be pretty easy to identify the local and absolute extrema. Okay, so let's start out by doing an extremely rough sketch of this function. So we know that we're increasing before negative 3. Increasing and then decreasing before 1, and then increasing again. All right. Okay, so let's see what this means. This means that f of negative 3, which what is f of negative 3? F of negative 3 is 6 times e to the negative third. This is a local max because the function changes from being increasing to decreasing. Okay, so how about f of 1? F of 1, which is equal to, what is it equal to? Negative 2 e to the minus 1 is a local min. Okay, so we've identified the local extrema. Our candidates were where our critical points were, x equals negative 3 and x equals 1. And we just tested to see whether the function was changing from increasing to decreasing or decreasing to increasing using the first derivative test. That told us the local extrema. Okay, so now what do we need to do? Well, we need to see whether or not one or both of these are absolute extrema. And now remember to do that, because the domain of this function is really an open interval, negative infinity to infinity, we really need to take the limits as x goes to infinity. Okay? So let's look. If we take the limit as x goes to infinity of f of x, well, e to the x is going to infinity, and x squared minus 3 is going to infinity. So f of x is equal to infinity. Okay, so what about the limit as x goes to minus infinity? Now this is a little bit tricky. Now why is it tricky? So if we just try to plug in minus infinity, or take the limit, e to the x is going to 0 as x goes to minus infinity, but x squared minus 3 is going to infinity. So we're getting something like infinity times 0. This is another example of an indeterminate form. So we're going to deal with indeterminate forms of this form in a later lecture, but for now we can actually just use algebra. So notice that if x is less than square root of 3, okay, then x squared minus 3 will be positive, e to the x will be positive, and so f of x will be positive. But look at this local min. This local min is negative. So what we're saying is that as x goes to minus infinity, f of x is actually staying positive. It's never going to dip below the x-axis. But that means that this local min that is negative is actually the absolute min. So f of 1, which is negative 2 times e to the negative 1, is the absolute min. And now because f of x is going off to infinity, as x goes to infinity, there is no absolute max. Okay, so that's how it goes. So you see there's a lot of different pieces that are fitting into the puzzle of how we're able to describe this function. Now, we're not quite done, because we also want to be able to describe not just how a function, whether or not a function is increasing or decreasing, but actually how it is increasing. And so we're going to talk about this in the next lecture, but we really need information also about the second derivative as well.